Hello dear students, welcome you all. How is everyone? I hope all are able to listen me. Okay. So let us start today's class. So in today's class, we will continue the discussion of ESE prelims previous year's questions. Okay. So this is lecture number 4 of ESE prelims PYQs, and we are discussing the previous year's questions of first chapter, and this is the fourth lecture in this discussion. Okay, so today in this class we will be discussing ESE prelims questions of years 2015 to 2019. Okay, so let us start with the first question. First question: a mechanism shown in the figure consists of equally long steel and copper wires. Okay, so these are the equally long steel wire and copper wire which carry the applied load in equal shares. Okay, so if I have applied load P, let us say, so they will share this load equally. That means this wire will carry how much load? P by 2, and this wire will carry P by 2 load. Okay, so both the wires will carry P by 2 and P by 2 load. So load will be shared equally, so that means half load will be shared. Now what shall be the ratio of the diameter of the copper wire to that of the steel wire when both the wires undergo equal strains? So one more thing is given, that they are subjected to, they will be subjected to, or they will be getting equal amount of strain. Okay, the strain will be same. Okay, so here the force will be in this P by 2, and here the force in copper wire will be P by 2. So P by 2 force will be in both the wires. Okay, now deflection in steel wire will be equal to deflection in copper wire. Okay, so PL upon AE, P by 2 length of steel wire upon area of steel wire into Young's modulus of steel wire. So formula of deflection is PL upon AE. We'll use P by 2 here, length of steel wire, area of steel wire, Young's modulus of steel wire, and here in copper wire also deflection will be same. So P by 2 will be the force, LC will be the length of the copper wire, AC area of copper wire, EC Young's modulus of copper wire. Now area is different because diameter is different. Force P by 2 will be cancelled from both the sides. So P by 2 and P by 2 will be cancelled from both the sides. Length of both the wires is same. So LS and LC, they will be cancelled out. So area, okay, so ratio of diameter of copper wire to that of steel wire. So area of copper wire divided by area of steel wire is equal to Young's modulus of steel wire divided by Young's modulus of copper wire. Okay, so this is the ratio of area. So area will be in the ratio of their Young's modulus, right? So area can be written as pi by 4 diameter square pi by 4 d square. So pi by 4 dc square divided by pi by 4 ds square is equal to es upon ec, es upon ec. Now diameter of copper wire divided by diameter of steel wire, that will be equal to under root of ES upon EC. Okay, so this is the ratio of diameter of copper wire to diameter of steel wire. What is the value of ES given? ES is given as 200 gigapascal and EC is given as 100 gigapascal. So this will be under root of 200 divided by 100. So diameter of copper wire divided by diameter of steel wire, that will be equal to root 2. Root 2. Diameter of copper wire divided by diameter of steel wire is root 2. Diameter of copper wire divided by diameter of steel wire. Okay, so A, option A is the correct answer. Clear? Okay, let's move on to next question. For a given elastic material, the elastic modulus E is 210 gigapascal and its Poisson's ratio is 0.27. What is the approximate value of its modulus of rigidity? Okay, so elastic modulus is given, Poisson's ratio is given, we have to find out modulus of rigidity. So relationship between elastic modulus, Young's modulus and Poisson's ratio is E is equal to 2G elastic modulus, shear modulus is modulus of rigidity, है ना, 2G 1 plus mu. This is the relationship, so we have to find out G. G will be equal to E upon 2 1 plus mu. What is the value of E? E is 210 gigapascal. So 210 divided by 2 into 1 plus mu. 1 plus 0.27. Okay. So 210, that means 105 divided by 1.27. 105 divided by 1.27. This cannot be, this cannot be, this cannot be. Okay, so no need to calculate. We can just by looking at this value, we can find out, we can, figure out that correct option will be 83 gigapascal. Okay, let's move on to next question. Next question, what is the ratio of the strain energy in bar X to that in bar Y? So strain energy in bar X to strain energy in bar Y when the material of the two bars is same. Okay, so they are having, they both the materials are same. That means Young's modulus is same. Young's modulus is same. Cross-sectional areas are as indicated over the indicated lengths. So cross-sectional area for this is constant throughout and the cross-sectional area is A. And in this bar, for half of the length, cross-sectional area is A, and for remaining half of the length, cross-sectional area is A by 2. Okay, so strain energy stored in bar X, what is asked? What is the ratio of strain energy in bar X to that in bar Y? Okay, so strain energy in bar X will be equal to P square L upon 2AE. This is the basic formula of strain energy. Okay, here load will be P only. Okay, length is throughout the length L, area of cross section is same. So P square L upon 2AE. This will be the strain energy stored in bar X. Now in bar Y, we have to consider two parts, this part and this part separately. Calculate strain energy in both the parts and then add them. Okay, so here again P square, or let us say strain energy in part 1, strain energy in part 2. Okay, like this we'll calculate. So strain energy in part 1 plus strain energy in part 2. Okay, so what will be the strain energy in part 1? Strain energy in part 1 will be P square into L by 2 divided by 2 into AE. Okay, plus strain energy in part 2, P square into L by 2 square. Okay, length of this part is also L by 2 divided by 2 into what is the cross sectional area? A by 2. So A by 2 E. Okay, so P square L upon 4AE plus P square L square upon 2 2s are 4, 2s are 4, again 4AE. Okay, so this 2 and this 2 will be cancelled out. So P square, why L square is there? No L square. Okay, this will not be L square. So this will be 2AE, P square L upon 2AE, P square L upon 2AE. So P square L upon 4AE plus P square L upon 2AE, this will be 3P square L upon 4AE, 3P square L upon 4AE. Now, if we compare P square L upon 2AE and 3P square L upon 4AE, we will be getting strain energy in bar X to strain energy stored in bar Y will be equal to P square L upon 2AE divided by 3P square L upon 4AE. What we are getting? 2 by 3. 2 by 3 will be the correct answer. Correct answer will be option. Clear? So 2 by 3 is the correct answer. Next question. Lead as a material used in construction has Young's modulus 15 gigapascal and bulk modulus 50 gigapascal. What is the Poisson's ratio? Okay, so what is the relationship between Young's modulus, bulk modulus and Poisson's ratio? Relationship is E is equal to 3K 1 minus 2 mu. Okay, so from here we have to calculate mu. So E upon 3K is equal to 1 minus 2 mu. So mu is equal to E upon 3K 1 minus E by 3K whole upon 2, like this. Okay, so 1 minus E. What is the value of E? 15 gigapascal divided by 3 into K, bulk modulus is 50, into half. So this will be the mu. So 15, 5, 10, 1 by 10, 1 minus 1 by 10, 0.9, 0.9 by 2, 0.45. So we are getting mu as 0.45. Correct answer is option D. Clear? Very easy question. Let's move on to next question. For a block with Young's modulus of its material being 210 gigapascal and its Poisson's ratio being 0.25, when subjected to a stress system as shown in the figure, what is the magnitude of stress sigma for no strain along AB? Okay, so here a block is given. Young's modulus is 210 gigapascal, Poisson's ratio 0.25, subjected to a stress system. So stress system is like this. In x direction we are having tensile stress of 60 Newton per mm square, and in y direction we are having sigma only. Okay, so along AB there is no strain, so strain along AB is 0. So in x direction there is 0 strain. So what is the formula for strain in direction AB? That will be equal to sigma x. Let us write it as sigma x only. Okay, epsilon x. Okay, let us say this is x direction and this is y direction. Okay, so strain in x direction will be equal to sigma x upon E minus mu sigma y upon E for 2D stress system, right? So sigma x is given as 60 Newton per mm square. Young's modulus, what is the value of Young's modulus? Young's modulus, let us say E only, and this strain is 0 minus mu. What is the value of mu? 0.25 into sigma y is sigma divided by E. So E will come common, multiply by 0, it will be cancelled out. Sigma will be equal to 60 divided by 0.25, that means 60 into 4, so that will be 240 Newton per mm square. So 240 Newton per mm square will be the correct answer. Correct answer will be option D. Let's move on to next question. Statement 1. The failure surface of an axially loaded mild steel tension specimen of circular cross section is along a plane at 45 degree to the axis of the specimen. Failure surface of an axially loaded mild steel tension specimen. Okay, axially loaded, we are having mild steel specimen. This is the mild steel specimen. Okay, it is subjected to force in axial direction like this. Okay, so the question is saying that failure plane is at 45 degree. So in tension what happens? In tension it will be pulled, and mild steel is basically ductile material. Mild steel is, where is mild steel? Axially loaded mild steel. Okay, so mild steel, ductile material. In ductile material what will happen? It will elongate too much. Okay, and what will happen? Necking will happen like this. Necking. Okay, so in necking, after a certain time what will happen? It will fail like this. This type of failure will be called as cup cone failure, and failure plane is at 45 degree. So that means this is correct. Okay, this is true. Assertion or statement 1 is true. Let us see statement 2. The failure occurs on a plane of specimen subjected to a maximum shear stress. Okay, so tension is applied like this. At 45 degree we will be having maximum shear stress. Okay, so at 45 degree shear stress is maximum shear stress will be happening. Okay, so mild steel is relatively weak in shear. Yes, mild steel is a ductile material. Ductile material is weakest in shear. So at this plane, along this plane, shear is maximum and it is weakest in shear. So failure is taking place along this. Okay, so this is also true. This is also true, and it is the correct explanation also. That means option A will be the correct. Both statement 1 and statement 2 are individually true, and statement 2 is the correct explanation of statement 1. Okay, let's move on to next question. A solid conical bar of circular cross section is suspended vertically as shown in the figure. Diameter of the bar at the base D equals 100 mm. So this D is equal to 100 mm. Okay, this is conical bar. In 2D it is looking like a triangle, but it is actually a conical. Okay, conical. Okay, so diameter of the bar at base D equals 100 mm and its length L is 0.5 meter. 0.5 meter, that means 500 mm. Okay, so length is 500 mm. If Young's modulus is 200 giganewton per meter square and its weight per unit volume is 80 kilonewton per meter cube, the elongation of the bar under self weight is. So elongation under self weight is rho L square upon 6e. Okay, so rho L square upon 2e is for cylindrical bar, and 1/3 of that rho L square upon 6e, 1/3 of that rho L square upon 6e will be for conical bar. Okay, what is the value of rho? 80 Newton per meter cube, 80 kilonewton per meter cube. Let us write units also. Into length. What is the length? So length, let us take as 0.5 meter only. Okay, because here meters are there. So 0.5 meter whole square divided by 6 into Young's modulus. What is the value of Young's modulus? 200 giganewton. So here we are having kilonewton, here we are having giganewton. Okay, so let us convert that giganewton to kilonewton. So if we convert that giganewton into kilonewton, we will be multiplying by 10 to the power 6. Okay, now it has become kilonewton per meter square. Kilonewton per meter square. Now this meter square and this meter cube will be cancelled out. Meter square will be cancelled out with this meter, and here we are having meter square. So 1 meter and 1 meter will be cancelled out. Only 1 meter will be remaining. Okay, so it will come in meter only. Also kilonewton and kilonewton will cancelled out. Okay, so answer will come in meter. So when answer is coming in meter and option is in mm, we have to multiply 10 to the power 3. So let us multiply 10 to the power 3. So now this will become in mm. Okay, so 80 so 80 into 0.25 divided by 6 into 200 into 10 to the power 6 into 10 to the power 3. Okay, so let us calculate. $80 into 0.25 into 10 to the power 3 whole upon 6 into 200 into 10 to the power 6 will be getting 1.67 into 10 to the power minus 5. So we'll be getting 1.67 into 10 to the power minus 5 mm. Okay, so this will be the elongation due to self weight. Correct answer will be option B. Just a minute. Next question. A circular shaft of diameter d is made of a material for which Young's modulus of elasticity is E and Poisson's ratio is V. The ratio of flexural rigidity to torsional rigidity of the shaft is. Okay, so what is the flexural rigidity? Flexural rigidity is EI. Flexural rigidity is represented by EI, right? Okay, torsional rigidity what is torsional rigidity is represented by? Torsional rigidity is represented by GIP. Okay, now ratio of flexural rigidity to torsional rigidity. Okay, so EI divided by GIP. Okay, that we have to find out. Now what is the value of, okay, what is the relationship between E and G? Relationship between E and G, E is equal to 2G 1 plus mu. Okay, so this is the relationship between E and G. So E upon G will be equal to 2 into 1 plus mu. Okay, this is the relationship between E and G. Okay, now I have to find out ratio of these two. So EI upon GIP will be equal to, first E upon G. E upon G is 2 into 1 plus mu. 2 into 1 plus mu. Okay. Now I upon IP. What is the value of I? Pi due to the power 4 by 64. This is circular shaft, no? Okay. So I will be equal to pi d to the power 4 by 64, and IP will be pi d to the power 4 by 32. Okay, so here 2 and 2 will be remaining, so this 2 will be cancelled out. We will be left with 1 plus mu only. Okay, so EI upon GIP will be equal to 1 plus mu. So 1 plus mu or 1 plus V. Okay, here Poisson's ratio is represented by V, so it will be 1 plus V. Clear? Yes, correct. Okay, next question. Next question, a cubical element of a structural part made of mild steel is subjected to triaxial compressive stress. Okay, so this element is cubical element and it is subjected to triaxial stresses. Okay, so stresses in y direction represented by sigma 1, stresses in x direction are represented by sigma 2, and stresses in z direction are also represented by sigma 2. That means stresses in x direction and stress in z direction are equal. Okay, so if we consider this as a coordinate axis, this is x direction, this is y direction, and this is z direction. So sigma x is minus sigma 2, sigma z is also minus sigma 2, and sigma y is minus sigma 1. Okay, triaxial compressive stress as shown in the figure. The vertical compressive stress is sigma 1. The modulus of elasticity and Poisson's ratio are E and mu respectively. What should be the uniform lateral pressure sigma 2 in terms of sigma 1 and mu so that the lateral strain is prevented? Lateral strain is prevented, that means strain in x direction and strain in y direction is prevented. Okay, so if I do summation, strain in x direction is equal to 0. So strain in x direction 0 equal to sigma x upon E minus mu sigma y upon E minus mu sigma z upon E. Okay, this is the generalized Hooke's law. Now if I put all the values in generalized Hooke's law, sigma x I will represent by minus sigma 2. So minus sigma 2. Now E can be taken as common. Okay, common denominator. Minus mu. What is the value of sigma y? Sigma y is minus sigma 1. Minus mu, sigma z is minus sigma 2. Okay, now this will be 0. So sigma 2 will be equal to mu sigma 1 plus sigma 2. Okay, now we have to find out what? We have to find out sigma 2 in terms of mu and sigma 1. Okay, so sigma 2 minus mu sigma 2 will be equal to mu sigma 1. Okay, so from here sigma 2 can be taken common, sigma 2, and this will be mu sigma 1 divided by 1 minus mu. Mu sigma 1 divided by 1 minus mu. So this is the value of sigma 2. So sigma 1, mu sigma 1 upon 1 minus mu. Correct answer is option A. Option A is the correct answer. Clear? Let's move on to next question. Two similar bars of steel and aluminium are heated to a same temperature. Forces are applied at the ends of the bars to maintain their length unaltered. Two similar bars of steel and aluminium are heated to same temperature. Okay, they are heated to same temperature. When we will heat steel bar and aluminium bar, they will try to expand, or they will expand basically. Okay, then we have to apply the forces at the ends of the wire. So when they are expanding, we have to apply compressive forces so that their lengths are unaltered. So length will not change. Okay, now if the ratio of Young's moduli of steel and aluminium is 3, that means Young's modulus of steel divided by Young's modulus of aluminium will be equal to 3. Okay, and the ratio of the coefficients of thermal expansion of steel to that of aluminium is 0.5. So alpha steel divided by alpha aluminium will be equal to 0.5. What is the stress on the aluminium bar if the stress on the steel bar is 100 megapascal? So stress on the steel bar is 100 megapascal. Okay, so this is given. Okay, this information is already given. Now what we have to find? We have to find out stress in aluminium bar. What is the stress in aluminium bar? This we have to find out. Now thermal stress formula is alpha TE. Okay, so if I find out the ratio stress A upon stress steel, alpha A, temperature is same, temperature rise is same. Young's modulus of aluminium, alpha of steel, temperature, Young's modulus of steel. Okay, so T and T cancelled out. Now what will be the ratio of alpha A upon alpha S? Alpha A upon alpha S will be 2. Okay, so this will be 2 into EA upon ES will be 1 by 3. 1 by 3. So sigma A is equal to sigma S into 2 by 3. What is the sigma S? Sigma S is 100 megapascal. So 100 into 2 by 3. So sigma aluminium will be equal to 200 by 3. 200 by 3, that means 166. Sorry, 200 by 3. 66.67, yes, 66.67 megapascal. 66.67 megapascal. Correct answer will be option B. Clear? Yes. Let's move on to next question. Which one of the following represents constitutive relationship? What is the meaning of constitutive relationship? Vertical displacements in a structure. What do we mean by vertical displacement? If there is any structure, let us say like this, or structure is okay, let us say structure is like this. Okay, here load is applied. So vertical displacement in a structure. Vertical displacement in a structure. So thus vertical displacement in a structure is dependent on function of the Poisson's functions of the properties of material. Yes, it will depend on properties of material also, but it will depend on many other factors. Okay, so it is not depending only on the properties of material. Okay, so constitutive relationship is the relationship that will be because of the properties of material only, that those relationships which are based on the properties of material. Okay, so vertical displacement is not only because of properties of material, it will depend on many other factors, like what is the area of cross section, what is the lengths, various lengths, what is the amount of load. Okay, on all these factors it is depending. Okay, like rotational displacement in a structure. So rotational displacement is also depending on many factors apart from the properties of materials also. Okay, then system of forces and equilibrium. Okay, this is completely independent on the properties of material. Okay, here stress strain behavior of a material. So stress strain behavior depends only on properties of material. Okay, so stress strain behavior is constitutive relationship. Okay, so constitutive relationship is stress strain behavior. Correct answer is option D. It is only depending on properties of material. It is depending on Young's modulus, right? Stress strain behavior. Hello Bhavika. Next question. Consider the following statements. Okay, consider the following statements. So let us consider these statements. In the infinitesimal strain theory, what is the meaning of infinitesimal strain theory? What is the meaning of, first of all, infinitesimal? Meaning of infinitesimal is very, very, very small. Okay, infinitely small. Meaning of infinitesimal is infinitely small. So infinitesimal strain theory means strains are very, very small, infinitely small. So in civil engineering structures also, in strength of materials also, we regard strains as very, very small. Okay, so the theory that we are talking about is infinitesimal strain theory. So in the infinitesimal strain theory, dilation is taken as invariant. What is the meaning of dilation? Dilation is volumetric change or volumetric strain. Okay, so change in volume or volumetric strain is called as dilation. So when we take strains as very, very small, very, very small strains, do we consider the volumetric change? No, na. Okay, now when we are considering deflections like this, okay, we draw, this is the value of deflection, this much is the deflection, but in actual practice deflection will be very, very small. Infinitesimal small deflections are there. So the change in volume of this material is also considered zero. We don't consider change in volume. Okay, so in infinitesimal strain theory, dilation is taken as invariant. Is it true or false? What is the meaning of invariant? Invariant means it is not changing. Okay, so we consider that volumetric strain is zero. Okay, so this is correct, this is true, first statement is true. Second statement, dilation is not proportional to the algebraic sum of normal stresses. Okay, so dilation, that means change in volume, delta V, it is proportional to algebraic sum of normal strains, epsilon x plus epsilon y plus epsilon z. Dilation is not proportional to the algebraic sum of all the stresses. It is proportional to sigma x plus sigma y plus sigma z 1 minus 2 mu divided by E. So it is proportional. So this statement is wrong. So statement 2 is wrong. Dilation is proportional, na? Right? Next, the shearing modulus is always less than the elastic modulus. Shearing modulus, okay. So let us see the relationship between shearing modulus and elastic modulus. So E is equal to 2G 1 plus mu, okay. So shearing modulus is always less than the elastic modulus, okay. So G upon E, if we take G upon E, we will be getting 1 upon 2 1 plus mu. Okay, so now we have to find out if this value is greater than 1 or less than 1. Okay, so if we see 2 into 1 plus mu, this is greater than 1, multiplied by 2, this is also greater than 1. So this denominator is always greater than 1. That means this value is always less than 1. If this value is less than 1, so G is equal to E into something that is less than 1. That is something less than 1. So G will always be less than E, yes or no? G will always be less than E. So shearing modulus is always less than the elastic modulus. This is correct. Okay. So 1 and 3 are correct. 1 and 3 are correct, but 2 is wrong. So none of the option is matching. So none of the option is matching. None of the option is matching. So what we should do? Dilation is not proportional to the algebraic sum. It is proportional. Okay. So there is some mistake in the question. Hi Ashwini. So there is some mistake in the question. Actually, 1 is correct, 2 is wrong, and third is correct. Okay. So what can we do? Let's move on to next question. Okay. Which of the following statements are correct? Let us see which of the following statements are correct. Strain in the direction of applied stress is known as longitudinal strain. Yes, that is correct. Strain in the direction of applied stress, in whatever direction we apply stress, in that direction it is called as longitudinal strain. Tensile stress results in tensile strain in linear and lateral direction. No, tensile stress results in tensile strain in linear direction. This is correct. This part is correct. But in lateral direction, tensile strain will cause compressive strains. Okay, compressive strains. So this part is wrong. So option 2 becomes wrong. Okay. Hello, Ashu. Next, third, strains in all directions perpendicular to the applied stress are known as lateral strain. Yes. So perpendicular direction, strain in perpendicular direction to the applied stress are known as lateral strain. This is also correct. Statement 3 is also correct. Fourth, ratio of change in volume to original volume is known as volumetric strain. This is also correct. So 1, 3 and 4 are correct. 1, 3 and 4 only. Option B is correct, right? Option B is correct. Okay. Next, the longitudinal strain of cylindrical bar of 25 mm diameter and 1.5 meter length is found to be 3 times its lateral strain in a tensile test. What is the value of bulk modulus by assuming E is equal to this? Okay, so value of bulk modulus. What is the relationship between bulk modulus? What is the relationship between bulk modulus and Poisson's ratio? So E is equal to 3K 1 minus 2 mu. Okay. So bulk modulus we have to calculate. So K is equal to E upon 3 1 minus 2 mu. Now Young's modulus is given. Young's modulus is given. What is the value of Young's modulus? 1 into 10 to the power 5 divided by 3 into 1 minus 2 mu. Now we have to calculate value of mu. So longitudinal strain is equal to 3 times the lateral strain, 3 into lateral strain, and we know ratio of lateral strain divided by longitudinal strain is equal to Poisson's ratio mu. Okay, and this lateral strain upon longitudinal strain will become 1 by 3. From here we'll get it is 1 by 3. So 1 minus 2 into 1 by 3. So what we'll be getting? 1 minus 2 by 3, that means it will be 1 by 3. 1 by 3 into 3 cancel out, and we will be getting K is equal to Young's modulus. So we'll be getting 1 into 10 to the power 5 Newton per mm square. Okay, so correct answer will be option C. Option C is the correct answer. Clear? Done? Let's move on to next question. For an elastic material, Poisson's ratio is mu. Modulus of elasticity is E. Modulus of rigidity is C. Bulk modulus is K. Mu is expressible in terms of K and C as. Okay. So K and C. K is bulk modulus. C is shear modulus. Okay. So mu 3K minus 2C upon 6K plus 2C. Okay, so this is the relationship. Let us see which relationship is 6K minus 2C wrong, 6K plus 2C wrong, 3K minus 2C upon 6K plus 2C. Correct answer is option C. Option C will be the correct answer, right? Next question. A mild steel bar of 450 mm, length 450 mm, tapers uniformly. The diameters at the ends are 36 mm and 18 mm respectively. So mild steel bar tapers uniformly. This is 36 mm diameter bar. This is 18 mm. Okay. Length is 450 mm. An axial load of 12 kilonewton is applied on the bar. E is equal to 2 into 10 to the power 5. Elongation of the bar will be. So elongation, what is the formula? 4pl upon pi d1 d2 e. 4pl upon pi d1 d2 e. Okay. So 4 into P. What is the load? 12 kilonewton. So 12 into 10 to the power 3 into length is 450 divided by pi. D1 is 36, D2 is 18, and Young's modulus 2 into 10 to the power 5. Okay. So 12, 36, 12 and 36. Let us cancel them out. Here we will be getting 3. Okay. Now 453, this will be 150, 150, and 350, 3, 6. Okay. 2, 2, 2, 3. So what we are getting? We are getting 50 upon 3 pi. 50 upon 3 pi. Let us count zeros also. Here we are getting 3 and 1, 4 zeros. So 5 upon 3 pi into 10 to the power 4. 4 zeros at top and 5 zeros at bottom. Here 10 to the power 5. So 50 for 5 upon 3 into pi into 10. So 2, 1 upon 6 pi. We'll be getting 1 upon 6 pi. Correct answer will be option B. 1 upon 6 pi mm. Right? Next question. A mild steel bar 1.5 meter long a mild steel bar 1.5 meter long has square section 40 mm into 40 mm. Okay, the bar is subjected to a two-dimensional stress. Sigma x is equal to this much, sigma y is equal to this much, Young's modulus this, Poisson's ratio this, the elongation of the bar in the direction sigma x. So elongation of the bar delta x. Okay, so that will be strain in x direction into length, strain in x direction, right? Now we have to calculate strain in x direction. So strain in x direction can be calculated by using generalized Hooke's law. So that will be sigma x upon E minus mu sigma y upon E minus mu sigma z upon E. Okay, so what is the value of sigma x? Sigma x is given as, okay, two-dimensional stress is given, so this can be removed. Sigma x is 310 tensile, so it will be positive. Okay, minus mu is 0.3. What is the value of sigma y? 300 whole upon E. Young's modulus. What is the value of Young's modulus? 2 into 10 to the power 5. Okay, so 300 minus 90. 310 minus 90. 310 minus 90 means 220. 220 divided by 2 into 10 to the power 5. So 110 divided by 10 to the power 5. Okay, so this will come in Newton per mm square. It will come in mm 1.5. Okay, so this is the strain, value of strain. If we have to calculate change delta x, that will be strain in x direction into length. So what is the strain? 110 upon 10 to the power 5. What is the value of length? 1.5 meter. Converting into mm, this will be mm. Okay, so how much we are getting? Here at the top there are 4 zeros, here 5 zeros. Okay, so 1.1 into 1.5. 1.1 into 1.5. 165. 1.65. 1.65. 310 minus 0.3 into 300. We are getting 220. That is correct. So 110 divided by 10 to the power 5, 1.5. 110 into 1.5 divided by 100. What we are getting? 1.65 we are getting. Answer is not matching. 1.65 mm. Let me check. One 1.65 mm, no? Just let me check, okay? Let me verify. Just a minute. Okay, sorry, one mistake. This is compressive. Okay, so it will be minus 300. So minus and minus, it will become plus. Okay, so 310 plus 90, it will be 310 plus 90, and if I do 310 plus 90, it will become 400. 400 divided by 2, so this will become 200 into 1.5 into 10 to the power 3 divided by, so this will become 3 mm. Okay, correct answer will be option D. Okay, so this is compressive. We have to pay special attention to sign convention, right? Yes. Next, statement 1. The failure of a mild steel specimen of circular cross section subjected to a torque occurs along its cross section. Failure of mild steel specimen. So mild steel is ductile material. Ductile material is subjected to a torque. Okay, so how will be the failure of this shaft? When ductile shaft is subjected to torque, what will happen? It will be subjected to pure shear, and ductile material is weakest in shear, and shear stress will be maximum at this plane, 90 degree to the axis. Okay, so it will be, the failure will be at the plane perpendicular or along the cross section. Okay, so subjected to a torque along its cross section, the failure of a multisteel of circular cross section subjected to a torque occurs along its cross section. So failure is occurring along the cross section. Yes, this is true. This is correct. It is true. Next, the failure occurs on a plane of specimen subjected to maximum shear stress. Yes, maximum shear stress. This will be the plane subjected to maximum shear stress, and mild steel is relatively weak in shear. Okay, so this is also true. This is also true. So both the statements are true, and it is the correct explanation also. Okay, it is the correct explanation also, right? So correct answer will be option A. Option A will be the correct answer. Okay. Yes. Let's move on to next question. What is the stress at the section XX? So this is the section XX, and we have to find out the stress at this section. So stress at the section XX for the bar ABCD with uniform cross section 1000 mm square. Okay. So area of cross section is given. First we have to calculate force at this cross section XX. Okay. So what will be the force? What will be the force at this cross section? Now this 110 kilonewton, this is tensile, and this 30 kilonewton compressive. So we'll be getting 80 kilonewton tensile. And if we check from here, 60 plus 20, 80 kilonewton will be tensile. Okay. So force at section XX will be equal to 80 kilonewton. That will be tensile, positive. Okay. Area of cross section will be equal to 1000 mm square. 1000 mm square. So stress at the section X will be equal to Px upon area. Okay, what is the force? 80 into 10 to the power 3 Newton. This is the force. And what is the area? Area of cross section is 1000. Okay, mm square. So 80 Newton per mm square will be the stress. 80 Newton per mm square tensile. Correct answer will be option C. As force is tensile, stress will also be tensile. Okay. Next question. The total elongation of the structural element fixed at one end, free at the other end, and of varying cross section as shown in the figure when subjected to load 2p. Okay. So total elongation we have to calculate. How we can get total elongation? Total elongation, let us say, considering this part as 1, this as second part, this is third part. So how can we get total elongation? In order to get total elongation, we have to calculate elongation of this part first, then elongation of this part, then elongation of this part, and then add all the elongations. Now, at all the parts, the force acting is 2p. Force is 2p. Okay. So total elongation is delta 1 plus delta 2 plus delta 3. Okay. Now force is 2p. What is the value of delta? PL upon AE. Okay. Now for first part, what is the force acting? 2p. So 2p, what is the length? L divided by area A divided by Young's modulus E plus delta 2. For delta 2 we are having area 3A, length L. Force will be 2p for all of them. Length will be L for all of them. Area is 3A. Young's modulus is E plus for delta 3 we are having 2p into length is L divided by area of cross section will be A by 2 into E. Okay. So we'll be getting, if I take PL upon AE common, PL upon AE I am taking common. So 2 plus 2 by 3 plus 4. 2 plus 2 by 3 plus 4. Right? So I'll be getting 2 plus 2 by 3 plus 4. So 2 plus 4, 6. 2 by 3 is 0.66. So I'll be getting 6.66 PL upon AE. 6.66 PL upon AE. Correct answer will be option A. Clear? Yes, we'll sum all of them. Right? Next question. A chain working a crane has cross-sectional area of 625 mm square. Okay, so this is the cross-sectional area and transmits a load of 10 kilonewton. Okay, so load transmitted is 10 kilonewton. When the load is being lowered at a uniform rate of 40 meter per minute, so there is a crane and crane is lowering a load at this rate. Okay, cross sectional area of the chain. So load is being lowered through a chain and cross sectional area of chain is this. Load lowered is 10 kilonewton. Okay, when the load is being lowered at the rate of this, the chain gets jammed suddenly, at which time the length of the chain unwound is 10 meter. So length of the chain at that time is 10 meter. Assuming Young's modulus is 200 gigapascal, stress induced in the chain due to sudden jamming is. Now here in this type of questions, there is sudden jamming, so it will be impact load. Okay, so in this type of question, in impact load, we have to equate the strain energy. Okay, so strain energy, whatever is the strain energy stored in the chain, should be equated to whatever is the kinetic energy. Okay, so the load was lowered at 40 meter per minute. So this is the velocity, and suddenly it is stopped. Okay, so whatever is the was the kinetic energy. Now when suddenly it got jammed, that kinetic energy becomes zero, but that kinetic energy will be converted into strain energy stored in the chain. Okay, so kinetic energy lost, okay, will be equal to strain energy stored in chain. Okay, so what is the kinetic energy? Half m into v square. Okay, strain energy stored is half sigma square upon E into volume. Is there any problem in this? Sir, please, if possible, take spring class on YouTube. I will be taking spring. Spring will also come. Okay, one by one, all the chapters will be taking. Okay. Now see, kinetic energy, half mv square, and what is the strain energy stored in the chain? Strain energy per unit volume is sigma square upon 2e, right? And if we multiply the volume, then we'll be getting total strain energy stored. Okay. Now half and half will be cancelled out. This will be cancelled out. Okay. Now mass. Chain working has a cross sectional area this, transmits a load this, load is lowered at the rate this. Okay. How we can calculate mass? Kinetic energy. Because okay, so whatever is the weight that we have to consider. Okay, 10 kilonewton was the weight. Okay, 10 kilonewton was the weight. So okay, so mass of chain is not considered here. Okay, chain is considered as massless. Okay, weight, whatever was the weight that was being lowered, that we have to consider. Okay, okay, so weight is what? 10 kilonewton. 10 into velocity square. What is the velocity? Velocity is 40 meter per minute. So 40 meter per minute. Let us convert this into seconds. Okay, so 60 square. Okay, 40 meter per second square. Okay, meter per second and whole square. Okay, sigma, that we have to calculate, sigma square. Okay, Young's modulus is how much? Young's modulus is given as 200 gigapascal. So 200 into 10 to the power 3 megapascal. That means Newton per mm square into volume. Cross sectional area is 625 mm square. 625 mm square. Okay. Into length. Length is 10 meter. So 10 into 1000 mm. Okay. Here we have considered velocity in meter per second. And here we are taking in millimeters. Okay, Newton per mm square. So let us consider this 40 meter per second into millimeter only. So into 10 to the power 3. Okay, now square. Okay, so little bit calculation. So 10 into Okay, just wait a minute. See, this is mass has to be considered, na? But here weight is given, and weight is given in 10 kilonewton. So we have to consider this also in 10 to the power 3 Newton, and we have to convert. Okay, we will divide by 9.81 G. Okay, then only it will be converted into mass. Okay, so 10, large value is coming, I think. So 10 into 10 to the power 3 divided by 9.81 into 40 into 10 to the power 3 divided by 60 whole square. Okay, so this is 4530524440.8 is equal to sigma square into something something. Let us calculate directly. Just a minute. Okay, so let me multiply it by 200 into 10 to the power 3 divided by 625 divided by 10,000. I'm getting this much, and under root of this 3807 sigma value I'm getting 3807.58. Okay, sum 625 into 10 into 10 to the power 3. Young's modulus is 200, and 10 into 10 to the power 3 divided by 9, 40. Gigapascal converting to megapascal, Newton per mm square. Okay, so here, just a minute, 10 kilonewton converted into Newton divided by 9.81. Okay, 40 into 10 to the power 3 meter per second. Okay, square. Sigma E is 200 gigapascal, 625 volume, 625 mm square, 10 meter into mm converted. Okay, all things are converted. Then 3807.58 I am getting. Why this I am getting? Just a minute. This is kg. I'll have to put units also. Okay, I'll have to put units also. Then only we'll be able to solve it. This is a little bit complicated, no? Okay, so first, just a minute. Okay, just a minute. Sigma square is equal to mv square into E by volume. Volume means area into length under root. This will be sigma. Okay, this is sigma. Now sigma should come in Newton per mm square. Okay, now mass will be in kg, velocity will be in meter square per second square, E is Newton per mm cube. Here A area, this. Okay, so this will be in kg. Okay, so here 1 Newton should come, and here 1 Newton should come. Okay, when both the Newtons will be getting multiplied, we'll get Newton square, and under root of that we will get in Newton. Okay, then only stress will come in Newton. Okay, so 1 kg meter per second square is equal to 1 Newton. Okay, so mass will come in kg. So we have to, put values like that. We should get 1 kg meter per second square. Then we can write it in Newton. Okay, so sigma will be equal to mass. Okay, mass. What was the value of mass? Mass is 10 weight is given as 10 kilonewton. So let us convert it into mass. Okay, so it is in kilonewton. So 10 into 10 to the power 3 Newton, okay, divided by, I have to divide by 9.81 G, 9.81. So this has become kg. Okay, this is kg. This much is the mass. Okay, so mass into velocity square. What is the value of velocity? Velocity is 40 meter per minute. So let us convert this into 40 into 10 to the power 3 divided by minute. How many? Divided by 60 seconds. Okay, so this is meter per second and whole square into Young's modulus. Young's modulus is 200 gigapascal. So 200 into 10 to the power 3 Newton per mm square. Newton per mm square. Okay, whole upon A into L. Okay, so what is the value of area? 625 mm square into length is 10 into 10 to the power 3 mm. Okay. Okay. Now I want 1 meter here. This is mm per second, not meter per second. I have already converted. Okay. This has become mm per second. Okay. So let me calculate the value. Okay. What value I am getting? Value will be same. 10 into 1000, 10 to the power 3 divided by 9.81 into 40 into 10 to the power 3 by 60 square square into 200 into 10 to the power 3 divided by 625 divided by 10 to the power 4. So we are getting 1449678.11 into. Now let us see units. Mm square and mm square will be getting cancelled out. It can cancel out from here also, mm square and mm square. Okay. Okay. So what units we are getting? This is kg, kg here, second square here, Newton divided by mm cube. Okay. Now if we take 1 mm here, from here, if we take 1 mm, put mm square into mm, okay, mm, okay, let us multiply 1 meter here and divided by 1000 mm. If I multiply 1 meter in numerator and divided by 1000 mm, does it make any difference? 1 meter and 1000 mm, both are same thing. Okay, now kg meter per second square, this has become what? This has become 1 Newton. Okay, so I'll be getting 14497.678 Newton square per mm to the power 4 and under root of whole thing. Okay, so under root of this, one 120.41 Newton per mm square. Okay, so this is sigma. So this was a little bit tricky question because of units. Okay, because of units. So 120.4 Newton per mm square. Correct answer will be option B. Have you got it? Have you understood? Any doubt in this? Any doubt? Let's move on to next question. In mild steel specimen subjected to tensile test cycle, the elastic limit is raised in tension and elastic limit in compression is lowered. Okay, so this is called as Boschinger effect. Okay, so mild steel, okay, this is the tension test. Okay, so if I keep on increasing the limit in, if I load it beyond the elastic limit, okay, and if I cold work on this, then what will happen? The elastic limit in tension is increased, but elastic limit in compression will be lowered. Okay, so earlier elastic limit in compression was here, now the elastic limit is reduced. Okay, so this is called as Boschinger effect. In the direction of applied stresses, if I am increasing the elastic limit by loading it beyond the elastic limit, okay, then what will happen, that in opposite direction, in compression side, my elastic limit will be lowered. Okay, so this is due to Boschinger effect. Next question, a solid uniform metal bar of diameter d mm and length L mm hangs vertically from its upper end. The density of the material is rho Newton per mm cube and its modulus of elasticity is E Newton per mm square. Total extension of the rod due to own weight. Okay, so rho L square upon 2E, this is the total extension. This is the direct formula. Okay, so correct answer is option A. Next question, a bar specimen of 36 mm diameter is subjected to a pull of 90 kN during a tension test. Okay, extension on a gauge length of 200 mm is measured to be 0.089 mm. So 0.089 mm is the extension, gauge length is 200 mm. Okay, and the change in diameter is 0.0046 mm, so delta D is 0.0046 mm. Okay, and original diameter is 36 mm. Poisson's ratio, so Poisson's ratio will be equal to lateral strain divided by longitudinal strain. Lateral strain divided by longitudinal strain. So what will the value of lateral strain? Lateral strain will be change in diameter divided by original diameter. Longitudinal strain will be delta L by L. So L will go in numerator and delta L will be in denominator. Change in diameter is 0.0046 divided by original diameter is 36 into length 200 mm divided by change in length 0.0089. Okay, no, not 0.00, 0.089, 0.089. Okay, now if I remove 10 to the power minus 4 decimal places from here, I'll have to remove 4 decimal places from here also. So I'll be getting 46 into 200 divided by 36 into 890. 890. Okay, so 10 and 10 will be cancelled out. Here 10 gone, here 10 gone. Okay, so 46 into 20 by 36 into 89. Okay, so we can solve it. 46 into 20 divided by 36 divided by 89 will be getting 0.287. Okay, so answer will be 0.287. This is the correct answer. So option A is correct. Clear? Yes. Next question. Principal stresses at a point in a stressed material are sigma 1 200 Newton per mm square, sigma 2 150 Newton per mm square, sigma 3 200 Newton per mm square. Young's modulus is 210 kilonewton per mm square and Poisson's ratio is 0.3. Volumetric strain will be. I think the answer is wrong. All the options are incorrect. All the options are incorrect for this. Okay, let us check. So we have to calculate volumetric strain. Volumetric strain will be sigma x plus sigma y plus sigma z 1 minus 2 mu upon E. Okay, so what is the value of sigma x? Sigma x is sigma 1. 200, okay, plus sigma y, sigma 2, 150, plus sigma 3, 200, 1 minus 2 mu, 1 minus 2 into what is the value of mu? 0.3. 0.3 divided by Young's modulus. What is the value of Young's modulus? 210 kilonewton per mm square, and these are given in Newton per mm square. So 210 into 10 to the power 3 Newton per mm square. Okay, so let us calculate. 200 plus 200, 400 plus 150, 550. 550 into 1 minus 2 into 0.3, 1 minus 0.6, it will be 0.4 divided by 210 into 10 to the power 3. Okay, so what we will be getting? 550 into 0.4 divided by 210 into 10 to the power 3, 1.047 or 1.048 into 10 to the power minus 3. Okay, so this is the correct answer. No answer is matching. Okay, so sometimes this type of question, yes, 1.047, or if we round off, we'll be getting 1.048. Okay, so answer is not matching in this question. Next, a mild steel bar circular in cross section tapers from 40 mm. So D1 is equal to 40 mm, D2 is equal to 20 mm, length is 800 mm, 800 mm. It is subjected to an axial pull of 20 kilonewton. So pull is 20 kilonewton. Young's modulus 2 into 10 to the power 5. 2 into 10 to the power 5 Newton per mm square. The increase in the length of the rod. Okay, so delta L, change in length, will be equal to P 4PL upon pi D1 D2 E. 4PL upon pi D1 D2 E. 4P, what is the value of P? 20 kilonewton. 20 into 10 to the power 3, length 800 mm divided by pi D1. What is the value of D1? 40. D2 20. Young's modulus. What is the value of Young's modulus? 2 into 10 to the power 5. 2 into 10 to the power 5. Okay, let us calculate. So in numerator we are having 1, 2, 3, 4, 5, 6. 6 zeros in numerator, 7 zeros in denominator. So 1 0 extra. Okay, so into 10. Now let us cancel out. 4 and 4 cancel out, 2 and 2 cancel out, 8 and 2. So at top we are getting 4 divided by pi. 4 by pi into 10. This will be the 4 by 10 pi. So 2 by 5 pi. 2 by 5 pi. 2 by 5 pi. Correct answer will be option B. Right? Yes. Next question. The stress strain curve for an ideally plastic material. So what happens for an ideally plastic material? Although all the options are wrong. All the options are wrong. But in this case, we can choose one of the best suited answer. Okay, the most closest approximation. What will be the most closest approximation for ideally plastic material? So stress strain curve for ideally plastic material is like this. Ideally plastic material stress strain curve is like this. Okay, so what happens in an ideally plastic material? If we apply the load, stress will keep on increasing, but there will be zero strain. No strain is there. Okay, stress is keeping on increasing, but no strain. And after a limit, after a certain stress is reached, the stress is constant and strain is keeping on increasing. Okay, so this is the characteristic of ideally plastic material, stress strain curve of ideally plastic material. So this does not match, this does not match, this does not match. One material is having this part is similar. Okay, in this stress strain curve, this part is at least similar, na? This part is similar. So here what is happening, if we are applying the load, stress is increasing, strain is not increasing. Okay, strain is constant. But here it should be exactly horizontal. This is not exactly horizontal. So the closest answer will be this. Closest answer will be option C. but it is not exactly matching. So best answer we can choose here as C. Okay, exactly it should be like this, right? Next question. The deformation of a vertically held bar of length L and cross section area A due to its cell weight only. Okay, so if Young's modulus is E and the unit weight of bar is gamma, the elongation is gamma L square upon 2E. So gamma L square upon 2E, this is the elongation. Correct answer will be option C. So direct formula. Next question. For a material, modulus of rigidity G is 100 gigapascal and the modulus of elasticity E is 250 gigapascal. Value of the Poisson's ratio is. So we know the relationship E is equal to 2G 1 plus mu. So we can calculate mu E upon 2G minus 1. E upon 2G minus 1. Young's modulus is how much? Modulus of elasticity 250 gigapascal. 250 divided by 2 into shear modulus is 100 minus 1. So 1.25 minus 1 will be getting 0.25. Mu is 0.25. Correct answer will be option B. Clear? Next question. A bar specimen of 36 mm diameter is subjected to a pull of 90 kN during a tension test. The extension on gauge length. On this concept, so many questions are asked. Poisson's ratio we have to calculate. Okay, so delta D is given, diameter is given, delta L is given, and original length is given. We have to calculate Poisson's ratio. So Poisson's ratio will be delta D upon D into L upon delta L. What is the value of delta D? Change in diameter 0.0046, 0.0046 divided by original diameter is 36 mm. I think in 2019 this question is exactly repeated with values also. Values are also same. We have seen this question, na? 0.287. ESE 2019. Okay, so I think, okay, 2 times this is coming times. This is repeated. Okay, repeat question. This is repeated. So it is typed 2 times. Okay, no problem. Let's move on to next question. A steel rod 15 meter long is at a temperature of 15 degrees Celsius. Okay, so length is given, length of steel rod is given 15 meter, temperature is given as initial temperature is 15 degrees Celsius. The values of alpha and E are adopted. Okay, when the temperature is raised to 65 degrees Celsius. Okay, so what is the change in temperature? Change in temperature is 65 minus 15, 50 degrees Celsius. You can represent it by delta T or you can represent by T also. Okay, not an issue. What is the free expansion of the length? So free expansion delta L is equal to L alpha T. Okay, what is the length? 15 meter. So 15 into 10 to the power 3 mm. Alpha, what is the value of alpha? 12 into 10 to the power minus 6. Okay, temperature. What is the temperature? Temperature changes 50 degrees Celsius. Okay. So 15 into 10 to the power 3, 12 into 10 to the power minus 6 into 50. 15 into 10 to the power 3 into 12 into 10 to the power minus 6 into 50, 9. Okay, so 9 mm is the change in length. Okay, now what is the free expansion? Calculated. What is the temperature stress? Okay, and if this expansion of the rod is fully prevented, what is the temperature stress produced? So stress will be equal to alpha TE. Stress will be equal to alpha TE. What is the value of alpha? Alpha is given 12 into 10 to the power minus 6. 12 into 10 to the power minus 6. Temperature change is 50 degrees Celsius and Young's modulus given 200 giganewton per meter square, but here mega newton per meter square. So 200 into 10 to the power 3 we will adopt. 200 into 10 to the power 3. Okay, so 12 into 10 to the power minus 6 into 50 into 2. Let us first cancel out all the zeros. So 5 into 2, 10, 1 0. Okay, 2, 3, 4. 7 zeros. Okay, 7 zeros minus 6 zeros. Okay, so 12 is the answer. 120 mega newton per meter square. 120 mega Newton per meter square is the stress. Okay, so correct answer will be 9 and 120. Correct answer will be option B. Option B is the correct answer. Yes, very good, correct. Next question, a bar of uniform rectangular section of a bar of some word is missing, just a minute. Okay, of area A is subjected to an axial tensile load P, its Young's modulus is E, and its Poisson's ratio is 1 by m, its volumetric strain. So what is the volumetric strain? Volumetric strain is axial tensile load P. So load is acting only in one direction. Let us say load is acting in x direction, sigma x is there. Okay, so sigma x plus sigma y plus sigma z divided by E into 1 minus 2 mu. This is the formula. Okay, so here only axial stress is acting, that means sigma y is 0, sigma z is 0, and sigma x is P by A. P by A. So we'll write P by A E into 1 minus 2 mu. So in place of mu, I'll write 1 by m. So P upon AE 1 minus 2 by m. So P upon AE 1 minus 2 by m. Correct answer will be option C. Option C is the correct answer. Okay, so these were all the questions. I hope you are able to understand all this question. This class was helpful to you. Okay, and let's meet up in the next class. So next class will be on Thursday. Okay, so today is Tuesday, so our classes will be on Tuesday, Thursday. Where is the pen? Pen. Okay, so classes will be on Tuesday, Thursday and Saturday. On all these days classes will be held. So see you in the next class. Okay, bye bye, take care, we'll meet on Thursday. Okay, bye bye.